So, before we go into discussing this solubility chart, let's discuss a few terms. Perhaps you want to write it down in a notebook paper or on the back of your warm-up, but you do need this information for your test. Is that okay? All right. So, let's write down a few things. What is a solute? What is a solvent? And what is a solution? What is the solution, guys? Is it an element, compound, homogeneous mixture, or heterogeneous mixture? What is the solution? Anybody in class? Yes. It's a homogeneous mixture. A solution is always a homogeneous mixture. Sometimes the words are interchanged too. Instead of referring to it as a homogeneous mixture, they'll call it a solution. Is that understood? So, what is the solute and what is the solvent in a solution? Anybody? What is the solute? What is the solvent? Yes. Okay. So instead of understanding it like that, let's say solution is the smaller part and solvent is the bigger part. Now, do solutions have to be liquids? Do all solutions have to be liquid? No. So solutions can be solids, liquids, or gases. Is that right? Anybody has an example of a liquid solution? What is an example? Yes. Water, you can write a formula. Therefore, it is a, if you can write a formula, it is a compound. What is an example of a liquid solution? Lena? Huh? Food dye when it's thoroughly mixed up. Is that right? One of my chemistry 1 students was saying the minute you add the food dye into water, it's actually heterogeneous. If you uniformly mix it, then it becomes a solution. Correct? That is a good example. One more. Let's do something else. Yeah. Sugar water. Saline water. Alright? So, dye water mixed thoroughly. Is that right? Mixed up. Or you can have salt water, which is saline. Alright? Or you can have sugar water, which is all like all the sodas. Is that right? Coffee, tea, if you add sugar, it's all sugar water. Is that right? Which flavor has been added? Do you agree? Okay. Give me an example of a solution that's a gas. Example of a solution that's a gas. Yes, Natalie. Very good. Indeed. It is air. Alright? Air is an example of a solution that is gas. What is the solute? What is the solvent in air? What is the solute and what is the solvent? Yes. Nitrogen is the solvent. In air, nitrogen is the solvent. And what will be the solute? Oxygen and anything else in the air will be the solute. You understand? In salt water, of course, salt is the solute, water is the solvent. Is that right? What about a solution that's a solid? Give me an example of a solution that's a solid. Yes? Was it a solution? Was it uniform throughout? There were lumps of sulfur in it, right? You remember that, Neil? That's a heterogeneous mixture. We are talking about something that's uniform throughout. It should be a homogeneous mixture. What is an example of a solution that's a solid? Yes.
Salt, sugar, or something like that. Is it salt?
Yeah, perhaps you can mix it up uniformly. I'm not so sure if you can get that uniform of a distribution. Yes.
Soil would?
Huh?
Soil?
No, soil would be heterotropic. Contains many things and it's not uniform at all. So one of the examples, let me give you. Have you heard of alloys? Anybody knows what an alloy is? What is an alloy? It's a combination of two metals, brass, bronze, steel. All these are examples of alloys. So one common example is 14 karat gold. Alright? So if you have 14 karat gold, what is the solvent, what is the solute in 14 karat gold? Gold will be what? Solvent. People won't buy it otherwise, right? Gold is the solvent. What else do they add to gold? Pure gold is a squishy metal, guys. Silver. Alright? So silver is the solute. Gold is squishy. Did you know that? You can press gold, pure gold, if it's 24 karat gold. Yes, Rafael?
I watched a video about someone compressing gold, and they said it's like infinitely malleable.
Oh, infinitely. That's interesting. Well, if you get to the atomic layer, after that it's no longer single sheet. Yes.
I remember like the stack to put like a solid gold bar on a table and start like banging on its face.
Yeah. Gold is very soft. So no jeweler can make gold that's pure. Does that make sense? He has to mix in another metal, but it's so thoroughly mixed in that it's a uniform distribution. Alright? And you can actually separate the silver from the gold. Because it's a mixture, you just heat it up. The melting point of gold and silver are different. So you can separate gold from silver with whichever gold ornament you have. Of course, the design costs, you lose that money, but you can just recover pure gold if you want to. Does that make sense? Steel, of course, was one of the greatest inventions, right, of the century. Iron would rust. Is that right? Steel is iron with a few carbon particles, and there are many other metals that are added to it, and then it no longer rusts now. Isn't that amazing that we can have steel containers? All right? So these are examples of solutions that can be solids, liquids, or gases. Now, what is the one factor on which solubility depends? You look at the graph. How much of a solid dissolves in a liquid will depend on what? Temperature. Is that right? Generally, you can make three different types of solutions. What are the three types of solution you can make? You can make a saturated solution. You can make an unsaturated solution. And you can make a supersaturated solution. Okay? We are very comfortable with solutions being liquid, so let's discuss with respect to liquid solutions. What do you think is an unsaturated solution? So let's refer to the example of maybe salt being added to water or sugar being added to water. Which solution is called an unsaturated solution? What do you know about an unsaturated solution? Anybody in class? Yes, Erin, you want to say something? No? Yes, sorry. Very good. So, an unsaturated solution, if you have a container, all right, and this is water, you're adding, if you can add more to it at that given temperature and dissolve it, then it becomes an unsaturated solution. More solute can be dissolved. That is an unsaturated solution. What is a saturated solution then? Alison, what is a saturated solution in your opinion?
Well, unsaturated is when you can dissolve more solid, so saturated would be when you can.
Very good. Very good. I like that. So saturated would be when you dissolve the right amount of solute and no more can dissolve. Is that right? No more of solute can dissolve. And we are all referring to it at that particular temperature. Is that right? It's very temperature dependent. Do you guys agree? Solubility is temperature dependent. What is a super saturated solution, Natalie?
It's a solution that can't occur naturally because it's concentrated has something that is being saturated, like carbon dioxide and soda.
So how do you bring about a supersaturated solution? Is it one where your solute particles are sitting in the bottom? Is that what you would call a supersaturated solution? Say if it is salt in water, is your solute particle sitting in the bottom? Will that be a supersaturated solution? No, not exactly. Any time the salt goes and sits in the bottom, what is the type of solution now? Well, it's a precipitate, or in this case, it's not a chemical reaction, it's just salt, it's a physical change. The salt is just going and sitting down at the bottom. What does the mixture become if you have a layer of salt on the bottom and a solution at the top? It becomes heterogeneous. Is that right? It's no longer a solution. It should be homogeneous. Therefore, a supersaturated solution cannot have any salt particles sitting in the bottom. Yet it is a supersaturated solution. Is that right? Yet it is a supersaturated. As Natalie said, you have more of the solute than can be dissolved in that amount of the solvent. Is that right? How do you bring that about? How can you achieve or make a supersaturated solution? Gaurav?
And you control the temperature, so it, the limit of the salt, the limit of the fluid that can be added increases, and then you lower the temperature.
Very good, very good. Very simple concept. Let's assume a temperature. Let's say it's 30 degrees Celsius. All right? All these three are at 30. All right? So the way you bring about a supersaturated solution is you increase the temperature to what? To 50 or so. And then now can you add more of the salt and dissolve it, correct? And then you very, very slowly cool the solution. When you cool it to back to 30, it becomes a supersaturated. It's a very, very unstable solution. It's very unstable because at that particular temperature, more has been dissolved, correct? So you can do a few little things and then you'll find that it's unstable solution. If you take a drop of salt and add it to such a solution, guess what will happen? The whole thing, the salt will start to crystallize out. It will start to solidify. It's really cool to watch. Have you ever used, like they have these little little packets that will generate a lot of heat so that you can put it on your muscles when they are really sore. They have little buttons inside them and you click them and then you'll see that the whole thing will become hot and it will crystallize. Has anybody ever had experience using such packets? Similar? Alright? So the idea is that the solution within is supersaturated. But sometimes making of a solution process can be exo or endo. Alright? So this solution, it's a supersaturated solution. So even if you give it a little bit of a shake, like you press that button inside, what's going to happen? The crystallization process is so exothermic that the salt is coming out back as a solid that will generate so much heat which can be used to for the sore muscle. And then you can heat it, the little sachet again, and then because the temperature is high, what will happen to all the salt? That's solid now. It will dissolve again, and you get your packet again. And then you have the unstable solution. Isn't that a cool science thing? You know how they have all this, what is that show called? Where they make money by selling an idea. Shark Tank, you know? It's just the concept of a supersaturated solution that's exothermic that's been packaged. And now people buy it for sore muscles because it generates heat. All right? Science, you can get a lot of ideas doing all such things. Okay, do we understand these concepts? Let's move back and let's have kids answer questions. So, I do realize we have not done such naming, but kids are very good with how they tease out the information. Were you able to understand that sodium nitrate is NaNO3? All right? So, Wu, can I have you answer the questions? Before we move on, it is given per 100 grams of water. Well, water is a solid. Is that right? I mean, liquid, right? For solids, you use mass. For liquids, you generally use volume. They have given it per 100 grams of water. Why have they chosen mass of water? Yes. Water is a universal solvent. Very right about that. But why did they choose mass over volume? Yes. Density of pure water is what? 1. If the mass is 100 grams, what should the volume be? 100 milliliters. Is that right? It's easy to conclude that. But nevertheless, there is one other aspect that we may or may not be able to touch during the course of this year. If you go on to take AP chemistry, we'll understand that volume is subject to temperature changes. Mass is not. All right? So it's better to take mass rather than volume. Anyway, so going back to Wu, it is at 50 degrees. So I take 50. This is just a graph reading skill. Is that right? And I have sodium nitrate. Wu, 50 and sodium nitrate. How much do you think you can dissolve? How much? 115. Looks about right. Is that right? So you go across and that becomes 115 grams. Is that right? Okay, put that one. All right, now, what mass of KClO3 do you need to create a saturated solution at 40 degrees Celsius? This is KClO3. Is that right? So now know this. For a given substance, at any temperature, are you with me? If you get a point above the line, it's going to be a supersaturated solution. On the line is saturated, below the line is unsaturated. So, Young, what do you think it is for KClO3 at 40? What amount do you need to add? What do you think? You find KClO3, right, Young? You find 40, you go up, and you extend across. What is the amount? Huh? 15, 15, 16, all that is fine. Are we good? Allison, so you created potassium nitrate. Were you able to figure out that that was KNO3? All right? So this is potassium nitrate. Okay? So you are dissolving 120 grams in potassium nitrate. Are you with me? Are you all understanding? And then I come down. All right? What is the temperature? What is the temperature, Allison? 65 looks about right. Kids tell me 64, kids tell me 66. Everybody's going to get right. The next one is the estimated digit. Is that right? Natalie, so this is ammonium chloride and we are at 170. So at 70 and 50 grams, so I'm going to see the intersection of 70 degrees Celsius and 50 grams. Is that right? Are we good? Do we understand? And we are looking at ammonium chloride. Is this point above or below ammonium chloride? What kind of a solution did you make? It's an unsaturated solution. Are you able to decide that? Did everybody understand how I came to that conclusion? Anthony. So we are looking at ammonia. Guys, can I erase all this now? It's a little cluttered for me now. Alright? So I'm going to erase all this. And I have a question for the class. Alright? We are looking at ammonia, right? Most of the substances, the solubility increases with increase in temperature. Yes or no? But for ammonia, the solubility is decreasing. What could be the state of ammonia that its solubility is decreasing with increase in temperature? What do you think it is? It can be, I'm hearing something. Yes, Jan? The state of the substance. When I say state of the substance, I'm asking if it's a solid, liquid, or a gas. What could be the state of ammonia that its solubility decreases when the temperature increases? It is a... Well, let's look at this. Salt is a solid, KCl is a solid, ammonium chloride is a solid, it's a gas. Does it make sense? So what can you say about the solubility of gases with increase in temperature? It's going to decrease. Why does the solubility of gases decrease with increase in temperature? Yes? They are spread out, or in other words, even a small amount of increase in heat energy gives these particles enough energy to just shoot out of the solution and go into a gas. They go into the air. We are no longer in solution, right? But then when solids dissolve, most of these solids are ionic. What are ionic compounds? A positive charge is held together by the force of attraction of a negative charge. They're like magnets sticking to each other. Is that right? So only if you increase the temperature can you break them apart, and then they will dissolve. More the temperature, more you can break them apart, but they don't have energy to fly away because they're just ions. Is that right? So they'll sit in solution. Does that make sense? Solubility of solids will increase with increase in temperature, while the solubility of gases will decrease with increase in temperature. Are we understanding this? The class is very passive. I'm a little worried. It's early in the morning. I don't know if you guys slept. I know it's the end of the week. It's a Friday. All right? Kids are just like zoning out left, right, and center. Are you with me? Okay. Now, so we are with Anthony. So how much of ammonia can you dissolve at 10 degrees Celsius? What do you think, Anthony? How much can you dissolve? Which one am I on? 5. Because at 10, how much can I dissolve? 70. But the question is asking for how many grams of water? 200. That's been highlighted. Did you make a note of that? So it's 70 times 2, which is 140 grams. Yes, Anthony?
I don't get number 4. Why is it unsaid?
Because we are looking at ammonium chloride, correct? that is ammonium chloride. I look at 50 and 70, the intersection of 50 and 70. Alright? 70 degrees Celsius and 50 grams. Where is the point of intersection? Is it above, below, or on NH4Cl? Therefore, you are making an unsaturated solution. Do you understand? At that temperature, I have dissolved less than it can dissolve. Therefore, I have made an unsaturated solution. Is it making sense? Anybody else has any other question on this? Are we good with reading the graphs? This will be on your test. You will have to read a graph, a question like this. Do you understand? Yes, Claudia. Because this is reported for how many grams of water? But they are asking for 200. You have to read the question carefully. Every part of the question counts. Any other questions? Do we understand this? Okay, we are moving on. Can you please take out your hydrate pre-lab notes from last class? Can you try to fill in the blank here? Can you please try and fill in the blank here? Let me pause this for a couple things that I want to announce. I never did that. Okay, here are a few things I want to say. So today is what day? Today is Friday. I see you on the 31st again. Alright? 31st, you should be prepared for a quiz on moles and a hydrate lab test. Is that understood? We're going to do a little bit of mole problems. We're going to review that with respect to ionic compounds. You'll have a quiz on that. Alright? You guys picked up the study guide today. Is that right? The weekend is coming up. I thought I'll give it ahead of time. Alright? So when is your test? It's on the November 2nd. Next week, Thursday. Is that understood? Everybody okay with that? Now, if you go to November 2nd, I think 6th, 7th are student holidays. It's the end of the quarter. 2nd is the end of, 3rd is the end of quarter. It's an early release day. Is that right? I see you guys again on 8th, November 8th. That's when your scientist project is due. Alright? The in-class presentation of the scientist by groups is due on the 8th. Now, 2nd is your test. 3rd is early release. What is due on 4th on Google Classroom? What is due, guys? The final research plan is due on Google Classroom on the 4th at 10 p.m. Is that correct? I have written whoever has submitted a rough draft of the research plan, I have returned the grade back. Is that right? That grade is not going to go in my grade book, provided you make the corrections and turn in a final research plan on 4th. Is that right? When you turn in the final research plan, please upload it to ScienceTier also. Is that understood? Upload your final research plan to ScienceTier. Well, if you do not have a rough draft, do not upload straight to ScienceTier. The assignment that you submit on the 4th is going to be graded for accuracy, for timeliness, for everything. And that is the grade that will go in my grade book. Does that make sense? Anybody has any questions? Yes, Lena?
So it's not due tomorrow?
No, it's due on Saturday at 10 p.m. Well, I know November 1st was the ScienceTier one, right? I'm just going to say all my kids will upload it by 4th. The registration process was due by 1st. I'm just going to go talk to the teacher and say that's how I set it up. I'm going to give my kids till the 4th.
Okay.
Okay? You have to upload it in 2 different places, right? Where do you have to upload it? to Google Classroom and to Scientier. If you do not have a rough draft that has been approved by me, do not upload it to Scientier. All right? I don't know if you can pull it down and revise it in Scientier. Does that make sense? Any more? And also know that my grade book closes as of now. Whatever grades you have, that's the grade that's going to go in first quarter. If you take a hydrate slab quiz, a mole quiz, and a test all of next week, all that is going on second quarter. Does that make sense? Students need to have time to retake the assessment if they haven't done well. And if I close my grade book, it doesn't provide for that time. Yes or no? So all retakes, everything that is due for first quarter is due by next week, Thursday. Right? Next week, Thursday, everything is due, 2nd of November. That's the last day you have time to make up anything for first quarter. Am I clear about all these announcements? Okay. Let's go on and complete the, what? Do that. Go ahead and complete the fill in the blanks for the hydrate lab. You need this for the test. Yeah.
What days do you stay after school?
Monday, Wednesday, Thursday. Are we done with the fill in the blanks? Shall we go over it, guys? Shall we? All right, let's do this. The word bank is also given. So this is pretty much a review of the understanding of hydrates. Is that right? So, Thomas, a blank is an ionic crystalline compound that has a specific number of water molecules bound to its atoms. A hydrate is an ionic crystalline compound that has a specific number of water molecules bound to its atom. Molecules of water that become a part of the hydrate are called waters of, Tori? They're called waters of hydration. They are called waters of hydration. In a formula for a hydrate, the number of Erin, the number of water molecules associated with each, what do you think, Dylan? Associated with each? Very good. Let's understand what a formula unit is. Now, let me go somewhere to the bottom of this page and perhaps do it. All right? If the smallest particle for an element is an atom, if it's an element, the smallest particle is called an atom. But if it's a diatomic element, what is the smallest particle called? It's called a molecule. Or if you have compounds, compounds can be of two kinds. They can be ionic or they can be covalent. Now Mickey Mouse is a water, what? You call it a water molecule, because whenever atoms are held together by covalent bonds, which is also the case in a diatomic molecule, it's called a molecule. Does that make sense? But in ionic, what are they held together by? It's the force of attraction, like a magnet. Is that right? That's called the ionic bond. The unit that comes together. Now we have written various ionic formulas. Is that right? We also wrote Mg3, Mg3 and 2. Is that right? Did we do that? Such particles coming together, 3 magnesium atoms and 2 nitrogen coming together and forming a unit are called what? They're called formula units. Do we understand? These are the smallest particles and they have their names. in chemistry. Do we understand what are formula units? Okay, moving up. So the substance remaining after the hydrate has been heated and its waters of hydration released is called mohair. What do you think it is? Anhydrous, that's right. It's called anhydrous or anhydrate. It's also fine. The ratio of Rohina, the number of moles of the ratio of the number of moles of what do you think you can pick up from here? The number of moles of hydration. Is that right? We already did formula units. Number of moles of hydrate. Is the hydrate given? We can use it again. Moles of hydration to 1 mole of the anhydrous compound indicates the coefficient. Yes?
There's a water of hydration and a hydration.
Is there a water of hydration? Am I missing that because of that? Okay, so let's pull this down.
Water of hydration.
Yeah, water of hydration, I crossed that out unnecessarily. Is that right? These are water molecules, this is water of hydration. Correct? Water of hydration to 1 mole of the anhydrous compound indicates the coefficient of water that follows the dot in the formula of the hydrate. Because anhydrous form of the hydrate can absorb water into its, what is it, Katie? Into its crystal structure. The hydrates are used as desiccants. Is that right? Did I spell that right? Is it 2 C's? Desiccants, all right, which are drying agents. Have you ever used water bottles that have little packets in them? Little packets that will say do not eat, and then there are little like tiny beads like things in them. Have you seen it? Those are desiccants. All right. Now, many of the instruments that you buy will have it. Many ionic compounds can be used as desiccants because they can absorb the water. Is that right? Why do we need desiccants? Stop right. There's moisture in the air, it can cause a lot of damage. All right? So as long as the product is sold, they don't want the damage to happen due to water. Why don't we use ionic compounds widely as desiccants? Instead we use the silica beads as desiccants. They are used in chemistry labs and things like that, but not too widely in consumer products. Is that right? Why? Say that? Yes? Yeah, it's like some of them have their own adverse reaction to skin and all that. Is that right? Because of which we don't prefer them as for consumer goods. Does that make sense? But many of them are desiccants. All right. So moving on. I think we are skipping the naming of the hydrates. Is that right? We'll come back to it later on. Now these calculations are important. Okay? So I'm going to answer the first question. This is U1, right? And this is 6. Do you see that number? Is that kind of clear to you? It's 1 cobalt carbonate to which 6 water molecules are attached to 1 formula unit, right? So that is called the mole ratio of cobalt carbonate to water. Does that make sense? It's 1 to 6. Okay? Now, we did do these problems when we did person composition. We did a very similar hydrate problem before. Is that correct? Can you students please complete B, C, and D? Let me give you 3 minutes and then we'll come back and we'll No. Okay, it's recording now. All right, guys. Can somebody tell me for the molar mass, do we do one cobalt, one carbon, three oxygens? We look up the molar mass from the periodic table. Cobalt is 58.93, carbon is 12.01, oxygen is 16. This becomes 48, that remains 12.01, that remains 58.93. What does all this add up to? Anybody? Yes. 118.94, and then we do water, which is 2 hydrogen, 1 oxygen, and it will add up to 18.02. Is that right? Times 6, because there are 6 water molecules, and what does this mass become? 108. What do you do in order to find the molar mass? What will you do with the two parts? You add them together. Is that right? The water and the cobalt carbonate. And what is the total mass? What is it, Cody?
227.06.
I can't hear you.
227.06.
227.06 grams per mole. It's the mass of 1 mole of that compound. Can somebody help me determine the percent of water? Yes, Claudia.
You would add 125, 127.06, and then you have to multiply that by 100.
And that is equal to
47.
47.62 is the percent of water. Okay? Let's go to the back page. Now, we all did the hydrate lab. Is that right? Last class, we heated the hydrate and we drove off the water. Now, instead of using an evaporating dish, we used a test tube. Is that right? Ours was the test tube plus the hydrated, test tube plus the anhydrous. Can somebody tell me, if I know the mass of the empty test tube and the hydrate, the test tube and the anhydrous, how do I determine the mass of the hydrate? Hey, how can I help? Oh, awesome. Come on in. So, how do you think we can calculate the mass of the hydrate? Anybody in class? Yes, Young. We subtract? Yeah. So that is going to be what number? That's going to be 15.66. And what do I subtract out of it? I subtract out the mass of the empty evaporating dish, and that gives me what number? 2.04 grams. Is that right? What is this? This is the mass of my hydrate that I took in the lab. Is that correct? Everybody understand? Any questions? How do I find the mass of the anhydrous? Who's going to help me? I know the mass of the hydrate. Now I evaporate the water, and now I have to find the mass of the anhydrous. How do I find that, Anthony? So that's the mass of the test tube and the anhydrous. Is that correct? So I take 14.67 and subtract out the mass of the or test tube, right? We used a test tube, so what's that going to be? 13.62, and what is that answer? 1.05 grams. That's the mass of the anhydrous salt that was left behind. Is that correct? Correct? How do I find the mass of the water in the hydrate? I know the hydrate's mass. I know the anhydrous mass. How much water evaporated from the hydrate? How do I figure it out? Natalie? So I subtract the anhydrous from the hydrate, 1.05. That gives me what, Natalie? Let me write this properly. 1.05, and that's 0.99 grams. Is everybody in class understanding these calculations? Remember, we are taking a lab test, and you're going to have similar questions. Not only it's going to be on your lab test, it's also going to be on your test. If anybody is not understanding, you should be asking questions now. Are we clear about this? Okay. So now, this is all experimental data. Is that correct? So I know hydrate, anhydrous, and water. I have to determine the percent of water in the hydrate using my lab data. How do I determine the percent of water in my hydrate? Not Natalie again, somebody else. How do I determine the percent of water in the hydrate? Yes, Katie. I do not want my students being distracted because Ms. Rotella is here. I really want you to keep your minds thinking. We are going to have a lab test and a test. Ms. Rotella will not be there then when we are testing. Remember that. All right?
Show
Yes.
off to me. Show off. Tell me.
Yes. What mass, Katie? Mass of the water, because that's my part. What will I take as my whole? Very good. The entire mass of the hydrate. Is that right? That's my whole. Do we understand this? Part by whole times 100. What is the answer, Katie? 48.53%. We are calculating per 100. It is percent. Correct? Okay. I'm not going to try and answer this. Let me see if one of my students can answer this. Theoretical percent of water from 2, which was, where did we calculate this? Oh, look at them, flipping the page. Awesome. And the experimental percent of water from 3D, calculate the percent error in this experiment. How do we do this? And I need a student volunteer to tell me how it's done. All right, Claudia, what is the formula for percent error?
It's absolute value and
Let's say theoretical, because that's what it says here. Theoretical minus,
the actual.
which is the, well, theoretical is actually actual, so let's, which is, this is the experimental divided by theoretical times 100. What do I take as my theoretical value here? The question guides you, but you should be able to do it on your own. Yes, Tori. So you go to the previous page. Now, this is very guided. Is everybody listening? It tells you kind of go to number 2. Is that right? You will not get such hints and clues on your test. Let's think about it. All right? Quick. So let's think about it. Okay? When you know the formula of the hydrate, is everybody listening to me carefully? When you know the formula of the hydrate and you calculate the percent of water in the hydrate, that is always your what value? That's always your theoretical value because the formula is given. Correct? The percent of water that you determine from the formula is your theoretical value. Write that down. Why did I write it down here? I know this. Will you remember it once you walk out of class? Okay, write that down. Can we move on? Alright? So, when you get data like this from the lab and you calculate, that is what? That is your experimental. This percent of water is your experimental, correct? Now you calculate your percent error. What is the previous number? I forget that. 47.62. So will you substitute 47.62 minus, what is my number here? Minus 48.53 divided by what number? 47.62. And this is the absolute value, correct? Do we care that it's negative? Times 100. What is your percent error? 1.11? Amazing. 91. All right. So here is a practice problem. All right. I'm going to give you 3 to 4 minutes. All right. It's a very similar problem. Let's see if my kids are thinking I'm doing the problem. All right. We have 4 minutes to complete this. Okay, guys. I'm going to continue with this. Okay. So you have the hydrate. Is that right? You have the anhydrous. So you subtract and you get what? 0.73. Is that right? Is that right, Rohina? Water is 0.73 grams. And then you do 0.73 by 2 times 100. What is the answer, Rohina? 36.5%. Okay, guys, I need help. What is the molar mass of FeCl2? Ricky, what did you get?
I got.
Just FeCl2.
The whole, I got 163.07
163.07 for the whole one or just FeCl2?
for the, for FeCl2.
Okay, then the 2 water is going to be 36.02. Is that correct? So what is this then? 126.75. Is that right, Ricky? Just for FeCl2? Right?
Yeah.
Okay? Is that right? Whoa, this is wrong. This thing is not aligned properly at all. Okay. So then you add up and what do you get total?
163.07.
Now I find the theoretical percent of water. Is that right? 36.02 divided by 163.07 times 100. What is it?
I think.
It's 162.79.
106. 162.79. Is that right? Why is everybody, nobody's helping me? I didn't do the problem.
Ms.Geeta, it should be 36.04.
04, okay. So 36.04 divided by, can you see these numbers or not? Okay. 36.04 divided by 162.79 times 100. What is the answer? 22.14%. So now I calculate my percent error. Is that right? 22.14 minus 36.5 divided by 22.14 times 100, right? What is the answer? How much, Cody?
30.058. Because that's like for experimental minus
This is the experimental. Is it 36.5 or 05? 36.5. So you subtract 36.5. What is the answer, Cody? No negative. Remember, it's the absolute value. 64.86%. Does it make sense? Are there questions? Can I see a thumbs up if you're okay with it? The class is really quiet many a times. And I have no idea if kids are okay with it or not. Okay, let's move on. And we're going to get into some mole problems, guys. Let's do mole problems. And I have 8 minutes left of this class. Is that correct? Okay. So we have done mole problems before. Do you remember that? We did it for elements. Now what are we doing it for? We're doing it for compounds. We did it for elements. We're now going to do it for compounds. Remember, the monkey in the middle is always the mole. So when you do conversions, you can convert grams into moles or moles into grams. Is that right? Similarly, you can convert moles into particles, which can be atoms, molecules, formula units. Are we good? You can convert moles to particles or particles to moles. Do you go directly from grams to particles or particles to grams? You always have to convert into mole first. Are we good? Let's look at the first problem. All right? It says 21.5 grams. It's a potassium oxide. What is the formula for potassium oxide? K? Is it KO? It's K2O. Why is it K2O? Oxygen is a -2, K is a +1. So it's K2O. Remember, K is a +1, O is a -2. So we need to take 2 of this. Correct? To balance out. So now I have grams of K2O in the bottom. What am I converting it into? Moles. How do I find the mass of K2O? Where do I find it from? Using the periodic table. So on the side, I'm going to say there is 2K and 1 oxygen. The mass of K is 39.10 off of the periodic table, correct? The mass of oxygen is 16. What do these add up to? So 39 is what? 8178.20. Is that right? Guys, I don't even have space to do the problem. Can you work it out and tell me what the answer is? Anybody? What is the answer? So 2 times 39.10 plus 16. 78 point? Is it?
94.2, sorry.
What is it? 94.2. So 94.02 or 2? 2. Or 02, what is that? 2. So 94.2 is the molar mass of K2O. Is that right? Which is equal to 1 mole. Now you have 21.5 divided by 94.2. Grams cancel. Is that right? What is the answer then? You have to report to how many significant figures? 3 significant figures. What is your number of moles to 3 significant figures? Thomas, you're writing this down? You will have mole problems on your test again. The quiz next class will be on these mole problems. What is the answer here? If you divide, I'm looking for an answer if you divide. 0.228 is 3 significant figures, moles of K2O. Are we understanding how this problem is done? Is it making sense? Or in other words, if 94.2 grams is 1 mole, 21.5 grams is how many moles? Isn't that the problem? Right? Are we understanding? Is it making sense? Okay, let's go jump down to problem number 3. We are going from molecules to moles. Is that right? So I have, is it 4.5 times 10 to the 24 molecules? Is that right? I cancel out of molecules and I'm going to moles. Is that right? How many molecules make a mole? 6.02 times 10 to the 23 molecules make a mole. Is that right? Molecules cancel. What do I do with these two numbers? Divide. What is the answer to 2 significant figures? If I divide, put it in a calculator, what is the answer? How much? Point. It's only 2. 7, 4, 8. So it's 0.75. Is that correct? Doesn't look right. That's a 24 and that's a 23. Is that correct?
7.5.
It's 7.5. It's 7.5 moles is the final answer when you divide. Is it making sense? Or in other words, if 6.02 times 10 to the 23 is 1 mole, 4.5 times 10 to the 24 is how many moles? Is that the proportion we are solving? Does it make sense? Alright, let's come down to problem number 5. Okay, we're going to do problem number 5. Okay, so we are going from grams to formula units. What do we convert grams into first? Can I go from grams to formula units straight? What do I convert grams into first? Moles. Is that right? So here is my problem. 4.68 grams. What is the formula for potassium phosphide? K is a plus 1, P is a minus 3. K3P. This is K3P. So I have grams of K3P in the bottom. I'll try and convert it into 1 mole. I need grams of K3P. Will I get that from the periodic table and substitute there? Is that right? K3P contains, well, the bell is... I will post an answer key to this worksheet. I would like you guys to try it. Is that understood? Okay.